So I will tell you about massive black hole binaries in a new large volume hydrodynamical cosmological simulation called Asterisk. So we want to look at these black holes in this cosmological concept as primary sources for LISA and for multi-messenger astrophysics. There are also associated talks with more results, preliminary results from Asterisk, from Yiying Ni, Colin de Graaf, and Yanyin Chen, as part of the meeting. So I suggest you also look at those. Just as a very, very brief introduction to focus on to the topic, we want to understand black holes and how they evolve along our cosmic histories. And this is certainly one of the greatest theoretical and observational challenge that we have. And we know that black holes are certainly present in every galaxy today. We know about quasars in the earlier redshift, in the earlier universe, and even at the epoch of ionization, some rare first quasars. But despite their full importance in the galaxy formation and evolution, we do not yet know the correct paradigm for the formation, for the first seeds of these supermassive black holes, how they were created, and what is the full cosmic history and the merger histories of black holes across the full span that I'm showing here. So what we know for sure is that mergers are going to happen. Black holes will merge throughout. And so the next capabilities like Webb, Roman, and the next generation satellites will rapidly mature knowledge of galaxies and black holes across cosmic time. But it is really truly through gravitational wave detectors and most of all LISA that we conclusively solve this 50-year-old problem of understanding what are the seeds for and the merger history of the black hole population. So cosmological simulations are our primary avenue for understanding structure formation in our universe, from the very large scale to smaller scales. And this is sort of an overview of one of these, actually the Asterisk simulations, sort of going into the different scales that we are now able to resolve and the pieces of physics from gravity, we have dark matter, we have gas that cools, goes into galaxies, making galaxies and stars into galaxies, all the way into the black holes. So state-of-the-art cosmological hydrodynamic simulation are certainly a primary avenue for understanding structure formation from the very large scales to subgalactic scales. They constitute, therefore, our best tool and must-go-to tool for a most realistic understanding also of black holes and the connection to galaxy formation. Sort of as schematically shown here, the simulations provide these very large scales view of our universe, but within there we have galaxies with their own black holes, so we can predict direct merger rates across the large cosmological volumes, as well as electromagnetic signatures and counterparts, both for the AGNs involved in these supermassive black hole mergers and the galaxy host. So here is the Asterisk simulation, or a panel, a view, an overview of it. So Asterisk is about 360 megaparsec on the side, so it is one of the largest volume for this resolution, has about 0.3 trillion particles, and this is again showing sort of this multi-scale physics that we can capture, and Yiying will talk a lot more about the details of this. So from the very, very large scales of this cosmological volume into scales of galaxy clusters and galaxies, and even inside of galaxies. And throughout all of this cosmic history, what we're interested here is also black hole mergers, which we do follow. Black holes also swallow gas, they grow and they merge as subsequent to a galaxy mergers, much like is shown in these two examples here. So these are two hosts that were extracted here, which have black holes. As this movie rewinds, we'll see the two black holes are sitting in their own galaxy, the galaxies, and start orbiting each other, approaching their first passage, and in fact, the final merger of the galaxies and the final merger of the black hole. So this is a demonstration of how we follow the black hole mergers, at least at these scales, and as well as what kind of information do every single galaxy and black holes possess in the simulation. So we have a black hole mass that is tracked. Of course, the black hole mass increases as a result of accretion, and the accretion rate is shown in the bottom panel here for these two examples. And as the two black holes approach each other, they're accreting from the surrounding gas, they're growing at the same time. while they're inspiraling and finally going to the merger. We do follow a lot of these objects. We do have a lot of them. This is just a gallery, in fact, a video gallery, right, of all of a suite of different galaxy hosts which contain black holes and which are in the process of merging. The black hole, the galaxies are merged, and the black holes themselves are inspiring toward the center to eventually lead to a merger. As you can see, these are all the orbital inspirals in all these different environments, in all these different galaxy remnants, all extracted just as an overview from Asterisk. So Asterisk has galaxies, so Ying will talk about galaxy luminosity functions and other statistical properties of the simulation, which can be validated and compared to observations. I'll move on to talk a little bit more about the black holes. What have we done in Asterisk? So we've chosen a parallel distribution from which we draw the black hole seed masses. Typically, in many simulations of this kind, this large volume, the black hole seed is chosen to be just as one value at a fixed value, which is seeded at or in newly forming halos, right? For example, between 10 to the 5, 10 to the 6. Here we've chosen to sort of span across sort of the light to heavy seed that have been conjectured by drawing a parallel, which makes the less massive seeds more abundant than the heavy seeds. Okay, so it's a parallel distribution, no longer a single seed mass that is being seeded. And the significant other piece of that we've added, we no longer reposition black holes to their local potential minima. This drew the black holes to merge very, very quickly as they approach the potential minima, and sort of very much artificially. Now we've added, like in other work that has been done recently, and I'm sure will be presented here, we have added dynamical friction so we can follow the inspiral and the orbits all the way into the resolution limit of the simulation, sub-kiloparsec scales. So we have these orbits that have across this large volume simulation. We'll talk about eccentricities of these orbits and how we have a lot of these objects that we can now at least measure eccentricities for during this binary inspiral. Let me show you a little bit about the consequences of this new modeling for the parallel seed that we've implemented as an initial mass function for the black holes. And the resulting mass function is shown here. Colin will talk a lot more about this. So this is the number of black holes as a function of black hole mass. This is Asterisk in yellow with a black hole population that does indeed show the parallel seeding in this regime where in fact black holes have just been seeded in the simulation, although the simulation now has evolved. So there's a full suite of black holes that have then grown from their seed masses already. We are redshift 5, and we're comparing with the TNG, which instead has chosen, like many other models, to a single black hole mass seed. Okay, so it's very evident. We do agree pretty well as the growth proceeds. The seed mass is sort of somewhat erased as a consequences of various episodes of accretion, and a black hole population extends into the high masses. But it clearly has Asterisk this very large population of smaller black holes that we're able to follow. For example, we can look also now at the black hole mass function now of the merged black hole systems, right? As they enter a merger, what is the black hole mass that we have in the merger? And we notice immediately that a second fundamental feature of Asterisk, which is the effects of dynamical friction. Whereas here we have the total mass function that is shown up here. This is the total mass function for the merged systems, right? So these are only black holes that have undergone a merger around this redshift. And we see a very strong suppression, implying that indeed, and the suppression is mass dependent, right? Is much more prominent at the low masses where we expect dynamical friction to have even more of an effect in the shallow potential where these sea black holes are trying to merge. This is different, for example, in TNG 300, where the black holes were repositioned, and so we see the difference is not, the mergers are much more efficient, pretty much a fixed fraction of the black holes merge at the same redshift. So to go a little further into And to this, we can also look at the black hole merger rates directly. And because of this larger seed population, the black hole merger rates in Asterisk are actually much more numerous than in a simulation like Illustris, which had a seed black hole mass and a much, which is much larger, and therefore missed all that large population of smaller black holes. This is not to say, though, that at a fixed seed mass, the actually dynamical friction that we've implemented would actually lead naturally to a suppression of mergers. So this is an experiment here, is the number of mergers per unit volume as a function of redshift, and it's Asterisk and Illustris again. And now we take the same black hole mass seed that in the two simulations, right? So we start at the same mass cutoff, and we see that in Asterisk, given a same fixed seed mass, the black hole mergers, the number of mergers per unit volume, per unit redshift actually decreases as expected, as dynamical friction will lead to less efficient delayed mergers compared to the repositioning. So that's also very much promising, interesting, and expected result. So let me just end with now the predictions actually of Asterisk in terms of in the strain frequency plane of LISA, right, with the LISA sensitivity curve plotted here. This is the Asterisk population. So again, we have now spanning into the mass range, which occupies a lot of the frequency range available for LISA. Again, in contrast to TNG300, which had a much larger seed population, so that at the same redshift, if we consider the same redshift, many fewer events actually could be predicted to be in this LISA. This is again due to the choice of seed mass and the fact that finally with Asterisk, we are starting to explore, fill in the wedge of the LISA populations, and as well as the redshift dependence of the mergers, right? So we have mergers already that occur very early on with the smaller seed masses. And Colin will talk a lot more about this. So I'm running out of time, so I should thank you and definitely point you to talks by Yiying and Colin again.